Welcome to the tutorial on academic prototyping. So today our speaker is Andreas Zeller. I mean, most people are aware of Andreas Zeller's outstanding research achievements in the area of testing, debugging, and security. Indeed, he's an ESEC fellow. He received the ESEC Soft Outstanding Research Award, among many other awards. But today, Andreas is giving a tutorial on a topic of the highest importance for our research community, how to share basically tools and technology to enable replication and comparisons. Because indeed, Andreas has another outstanding talent besides research. Over the years, I've known him. I realized that he had that capacity to tackle complex issues, technical or not, and present them in a very clear and insightful way. And this is visible from his online books on debugging and fuzzing, but also from his many presentations to the community, like this one. And it's truly a rare talent that he has developed over the years and that we are going to benefit from today. So please do enjoy this important tutorial, and Andreas, the floor is yours.
Thank you very much, Lionel, for this very, very nice introduction. Thank you, Lionel. It's Lionel, right? Oh, thank you. Okay. I'm a bit loud here. I feel like a voice from above or something. Okay, good. So, welcome to my tutorial over here. We're in for 90 minutes of absolute coolness, which actually refers to the temperature in the room. So if you came here to relax a bit and just enjoy what's happening on the stage, well, you come to the right place. You can absolutely relax for 90 minutes, which is all fine, because, well, I'm not sure whether I'm going to tell anything new to any of you, so just relax and maybe just enjoy the show. Well, there's one way to do it. Another option is you can also make use of your arms, these extensions that you use to work with your mobile phones and your laptops and all. Who in here has a hand? Can we just check that? Okay, not everyone, I'm very sorry, but you can also raise your feet instead. That's another option. Okay, so but what I want to point out, I just learned that there's a sentence which says, you can interrupt me anytime during the talk. But this is bad because it has the word interrupt in it, in a meaning that is not necessarily systems programming, but this means, if I'm going to ask a question, I'm going to interrupt Andreas' flow of genius towards the audience, and the entire audience will also be interrupted, so I better not ask a question. Well, the thing is, I have prepared this tutorial. I only have prepared 20 minutes of this tutorial, which means that not only am I now talking forever before we actually get to the point, no, but this also means that all the remaining time is actually your time, meaning that you raise your hand and you can ask something stupid or you can ask something nice. The audience is going to decide on that, whatever. I'll be perfectly here for you, okay? So just raise your hand. I will notice that if you raise your hand, and at some appropriate time in the next minute or so, I'm going to take a break, and then you will be famous for 20 seconds. Okay, good. So we understood this. We know how to raise our hands. Yeah. I mean, normally it's you who stand in front of some students, and then they raise their hands and ask, Professor, shouldn't you have a semicolon over there or something like that? Yeah, sure. Of course you should have that. But you can also ask me whether there should be semicolons. Okay, good. Now, let's get to the meat of things here. Very simple. I have, in my life, I have made a couple of mistakes. And I have even passed on these mistakes to my PhD students. And not only have I lost years of my life, my PhD students also have lost years of their life. My aim today is to avoid you falling into the same trap that I have fallen into. Good. No, I'm not talking about drugs. I'm not talking about alcohol. I'm not talking about going for tenure. No, I'm talking about programming languages. Thing is, I'm working in program testing and debugging, program analysis, testing and debugging. And when I started my career, many papers in software engineering and programming languages essentially look like this. We have invented a new, whatever, pointer analysis, pointer aliasing method whatsoever. And here we demonstrate this on this little toy language, which consists of one assignment, one variable, one while loop, and that's essentially it. Okay. Well, also pointers, I guess. And it works. Here's the proof. Boom. Paper accepted. Wonderful. Then along came a guy named Walter Tichy, some 20 years ago, and told us all, should computer scientists experiment more? That's a very famous paper, probably one of the most influential papers in the history of software engineering. And you can only understand why it was influential if you compare the times before that paper with the times after that paper. And he essentially complained that many papers that came up in software engineering and programming languages and related fields came without any experiments on real-world software whatsoever. And this was about to change, because how do you know whether something really works if you don't apply it on real-world software? And then we got a big move towards actually applying our techniques on real-world software, which happened to be typically some open source software. Which then meant if you just declared, I have this new whatever points to analysis whatever, you wouldn't be, it wouldn't be accepted unless you evaluated it on 20 programs, 20 real-world programs first. And then reviewer 2 came along and told you to make this work on 40 programs, and then on 60, and then on 80, and then after that, reviewer 2 told you to compare against the previous approach, and you tuned your hyperparameters until it finally did. And then everything became hyperparameters, and we ended in this big ML show that we're currently having, but that's a different story. Thing is that making the shift from something that works on a toy language and only works on paper towards something that was to be implemented and work in real-world industrial environments, whatever they should be, was actually a major one. And then PhD students all across the world all of a sudden had to build software that was supposed to work on real-world programs. Now, there are things which are easy in software engineering, also in that field. And then there are things that are hard. For instance, well, whatever. Counting the use of emojis on Stack Overflow. Oh, that's a script, I can write this, that's probably easy. But getting, say, an automated testing tool or a big scale static analysis tool to work precisely on large amounts of Java code of industrial size, that's something that can easily set you back for years. And not just you and your PhD student, multiple PhD students, sometimes over multiple years. Ask Eric Bodden on his effort on Suit, for instance. We're all super thankful for his work. But yes, this is the work of decades. Okay, good. Again, compare counting emojis, building something in a decade of work, gets accepted. Well, you didn't compare against all the other approaches there. Good. Maybe there was work on emojis. I'm just pointing that out. Replace emojis with semicolons or anything else that you're interested in. We'll find that out. And I also feel guilty for having sent students into this, because the thing is, why do I feel guilty? Not so much because there would be something cool coming out at the end. But the thing is, invariably, we would have some PhD student working on some huge infrastructure. And invariably, there would be a huge steaming pile of code produced by this very PhD student, which ended up there when the PhD student would leave, and then you are faced with this huge steaming pile, and there's nothing you can do with it anymore. Maybe you can pass it along to the next PhD student who will spend a year just figuring out what this whole thing does, and how to use it, and how to invoke it. And the problem is particularly bad because we are in research. It's not like I'm coming to you with a specific set of requirements, build this, build that, build this other thing, and then a miracle will occur, and everything will work just fine, and you will get your paper published. No, this is not going to work. Because, well, it may not, your approach may not work, period. Or it may be worse than your competition. Or your paper will not be accepted, or your paper or your reviewer will demand, yeah, this works on Android, but does it also work on Linux? Does it work on Solaris? I'm a Solaris fan. Does anybody know what Solaris is? Well, maybe it's the biggest operating system on the planet, and I urge you to actually port it over there. Who knows? What I want to point out here is that you need to change, during a PhD or during research, you often need to change directions. You're building something first until it sort of runs. Then you find out, oh, I should have done this entirely differently. And then you have to re-implement large portions of things. And then you find out, oh, I should have done this differently again. And you again need to refactor the whole thing, move it into a different direction. And oh, it turned out you never thought about this particular change that you need to do in the first place. So you need to rebuild things from scratch. All this is very, very time consuming. And for us software engineers who teach about what to do in a world of changing requirements, of imprecise requirements, where we do not know what to come out, actually, this is not how we should do things. Actually, we're teaching people how to be agile. And we are teaching people how to build prototypes first to test the feasibility of an approach. And incidentally, this is what I'm going to talk about to you today. How to be agile during your research, and how to build prototypes that allow you to very quickly evaluate whether something works or doesn't. And I'm going to do this, and I'm going to do this using an example. I'm going to build an automatic test generator that automatically explores all paths of the program. Christian Kadar, are you here? Christian Kadar is the inventor of CLE, a big symbolic tester for C program. I always wanted to ask Christian, actually, how many decades has it taken you to build this thing? Decades, probably the wrong unit. It's something like, it must have been several years. And I'm going to show you the basics of this in something around 20 minutes. Building this from scratch with nothing but my bare hands and a copy pasting. Okay, good, I'm cheating here, but you're going to see that. The environment I'm using here, and here we go, finally, I need to fill this thing. You're not going to see any slide today. You're just going to see me coding, and that's going to be, and I hope that's going to be mildly entertaining for you. The environment I'm using here is Jupyter Notebooks, which is an environment where you can type in arbitrary, well, in this case, Python expressions and Python code, and you can evaluate them directly. These Jupyter Notebooks have their specific values and also their specific setbacks. This is not the most important thing here, but the most important thing here is that I'm using a language which allows me, which comes with a language which comes with a very, very big library of functionality, number one, and which B is extremely easy to analyze and to work with. And this language for me happened to be Python. That is the language that we use to teach to our beginners or data scientists. Well, this is how you build a Fibonacci function, whatnot. Do we still do that, Fibonacci functions? I'm not sure. Fibonacci faculty, whatever. These things, this is exactly the same language I'm using to build really complex dynamic and static and symbolic analysis in here. And I'm going to start with something simple that many of you may know. Here we go, here it comes up. This is the triangle program. So I'm not going to type this in because I'm a very slow typer in here. So let's see whether this works. Wonderful, wonderful. Okay, good. Triangle program takes, a triangle program is a program that takes three numbers, A, B, and C, which actually are which actually happen to be the lengths of the three lengths of a triangle, and it categorizes this triangle into multiple categories. For instance, if I give it a triangle with whatever 3 inches of length on each side, this is an equilateral triangle. Or if I go and, oh, well, we have this one. If I put in 2, 3, and 4, it's a scalene triangle. And if two numbers are the same, it should be in isosceles. Native speakers, is it isosceles? Isosceles? Isosceles. Oh, isosceles. That sounds cool. Sounds a bit Greek to me, but it's fine. Okay, here we go. And then you can simply go and invoke this. Now, if you want to test this program, here we go. You want to make sure that this is a classic in testing. If you want to test this program, you want to make sure that all the different behaviors of this program are covered, which means that, which translates actually in our program that you want to make sure that all branches are covered in the program such that every single return option here is covered at least once. And yeah, sure, the art of software testing now is to come up with appropriate numbers that actually cover all these different branches in here. However, building tests from hand has somewhat gotten out of fashion. Today we use fuzzing for such things, or that is, we use random testing. So let's start our exploration into fuzzing or into Python here with a simple, with a very simple. Oops, sorry, built the wrong thing in here. See, I'm always mistyping things. We can start and build a very simple, very simple fuzzer in here. Sorry, what am I doing here? Oh yeah, here we go. Okay, so I'm just creating 3 numbers between 1 and 10. And I'm doing the same for a second. And please let me know if I'm too fast in here, just in case. So rand range returns a number between the 2 arguments in here, between 1 and 10. And then I can just invoke the triangle function with A and B and C. This is Python, so we don't have to worry about declaring types, declaring variables, or coming up with anything more complicated. This is just a piece of Python that gets executed right while I'm working. And now all I need to do is I need to print out what the result is, which is not very complicated. Simply going to print out A, B, C, and T. Since this is Python 3, I need to put this in parentheses. Here we go. Wonderful. And now I can invoke this whole thing. And now we get, for the value 343, we get isosceles number 3. 521, this is a scalene triangle. 272 is another isosceles, triangle. Did we cover all different variations already? Well, come on, this is random testing. Here we go. And we can just create a few more. For some reason, I don't get an equilateral triangle. How many chances do I need? Oh, I'm going to need 100. Oh, I'm going to need 100 tests in order to get there. Well, actually, I have 100. Okay, well, there we go. Here is an equilateral triangle. So now we actually have covered all the individual branches in the triangle program. So that's very simple. Okay, this is just to get you, for those of you who don't know Python, this is just to get you into gear. So you have loops, you have invocations, nothing too complex in here. Okay, let's get rid of this thing again and let's go back to a smaller number. Okay, so that's a very simple way. You have functions, you have invocations, you have random numbers, and you can have fun with these. So, but this is something that you can do in any programming language. I mean, sure, I can do this in Java, in Fortran, and R, and BASIC if needed. So what's the special part about Python in here? Well, one thing is that for any kind of dynamic analysis, for instance, if you want to check whether specific values occur in your program or whether specific specific branches are being taken whatsoever, you need a dynamic analysis, an analysis that actually checks what happens while the program is being executed. And for this dynamic analysis, the usual way is that you need to instrument, so you need to extend your compiler such that it instruments the code, such that the necessary computations are then undertaken when the program executes. This is painful, and this is going to immediately set you back by weeks. In Python, this is something that is very, very easy, because we actually don't need much for that. There's a nice little function in there's a nice little functionality in Python, which allows you to actually very easily trace what's happening during a program execution. More specifically, you can define a function. I named this trace it over here. And this is a function that will be called for every line of execution of the program. So this will be called for every line, and then we can, for instance, log what's going on while the program is executing. Most notably, we can access the name of the function that's currently being executed. So this is how we do that. Oh yeah, this actually, well, was all correct. So there we go. Function code. We can also extract the name of the function. If I recall this right, this is function code.coname. Here we go. And I can also extract the current line number. Here we go, line number. If I'm too slow for you, I'm going to speed up things. No problem. If I'm too fast, I can also, I can also slow things down. And interestingly, you can also extract all the variables from the program. We'll come to this in an instant. Okay, and now that I have all this information, I can, for instance, go and say, okay, I'm interested in the function name and the line number. There we go. Lionel number, no, that's line number. There we go. This is all we need. And in the end, the function has to return itself. So there we go. This being Python, we don't yet necessarily know whether the code is actually correct until we execute it. The benefits of static analysis. And now I can create a very simple variant of my triangle function. Triangle traced. Oh, let's give this actually we can insert parameters later on. So let's define this. And now comes the magic. There's a function which says I want to define a trace function. Sys.set trace it, and then we do triangle. Well, I just need to invoke it. Triangle 2 to 1. Here we go. And after that, we're done with tracing. We turn tracing off again. Okay, now comes the magical moment. I just wrote that code, but I haven't tried it yet, whether it actually works. So now if I invoke triangle traced, this should turn on tracing up here and define the traceit function, which we have up here, as the tracing function, namely that this is now going to be executed for every single line. And then I invoke triangle, and while triangle is being executed, this traceit function should also be executed, and namely for every line, and print out the current name and the line number. So let's see whether this works. Chances are 50% that we're going to get into some typing error of mine. Yes, wonderful. Got it. What did I do wrong? Frame F is not defined. Oh, frame. How is that possible? Oh, it's not frame F. Yeah, of course. It's frame F underscore code. That's how you do it. Thank you so much. And yes, this is it. Try it. Oh, here we go. Wonderful. Now it works. So if I invoke triangle program with 2, 2, and 1, the first line of triangle gets executed, then line number 2, then line number 3, and then line number 6, and then line number 6 again. 1, 2, 3, and 6. Which ones are these? This is line number 1. This is 2. This is 3, 4, 5, 6. Isosceles number 1. This is the line that's executed, and this should also be the one that is returned in the very end. Well, I guess I should have printed that out. Okay, print. Oh, no, that's a bad idea. I don't want print to be traced here. So we just print the return value. There we go. Isosceles number 1, that's good. Or even better, return red, that's better. Okay, exactly as it should be. So, and the value that you see up here, by the way, is the return value of the function that we have up here, which is triangle. Okay, now we can actually print out more stuff. We can actually also go and find out what is the current line that's being executed. So for this, we can easily inspect the code. So for this, we need the source lines, and this is actually something I'm simply going to copy from my Scratchpad down here. Here we go. Far easier, because I don't want to type all of this in here. There we go, boom, and we go back to our original code. So when I'm going to insert all of this big blob here into my code, there we go. And what I'm accessing now here is a bit of more information, because that's something, yep, that is also something that works extremely well in Python. I can simply go and say, okay, give me the source lines of the current function that I'm executing. And when I have the and give me the starting line number, and then I can actually print out the current line that is being executed. And this is all super useful. And on top of that, I can even print out what are the values of individual variables, which actually boils down into the following. Now, if we invoke this, we're going to get a more detailed trace, which is actually pretty neat. So now not only do we see the name of the function and the line number, we also see the code that's being executed. And on top, we also see the names of all variables. So if I wanted to build something like statistical fault localization, okay? Program spectrum. I want to count how often a particular line is executed. I want to associate the execution of a line with whether a program fails or whether it passes. I want to check variable values. I want to find out, I'm using machine learning. I want to figure out, is this return value of equilateral actually somehow connected to the values of the variables A, B, and C? And I'm going to kick off my huge deep neural network to find out whether there is a relationship. Hint, there is. If all 3 values are 2, then it's equilateral. I can do all that because I have all this information on my hands. And the 3 lines, this set trace thingy, which are just inserted here, is something I can do for arbitrary Python programs. If you have a web server that's written in Python, if you have Netflix is mostly written in Python. Well, not the part that actually streams the videos to your home, that would be vastly inefficient, but all the glue code around, all that is all Python. And if you want to find out anything about, about how the individual parts of Netflix work, well, it takes 3 lines of code to actually turn on tracing, and well, 7 more lines to collect this. The simple act of producing a listing like this, getting a trace of what's going on in a program, again, in C, in Java, is something that's going to set you back for weeks, if not months, if you want to build this from scratch. If you ever wondered why we have, say, fuzzers that are driven by code coverage, why just code coverage? Why not say trying to find out as many values as possible? Why not trying to fill this buffer with as many zeros as we can and guide search towards that? Well, the answer is simple. We do have tools for measuring coverage, and this is what we use. And building any other tool takes months, so we don't do that. But with Python, you can easily, I could now easily go and say, okay, I'm going to use these. I'm going to use this functionality. I'm going to extract variables, and I'm going to find out which values occur in failing runs, in passing runs, whatsoever. I see occasionally raising hands, but yep, no, but you're just rearranging your hair. That's fine. Thank you. Okay, but no questions so far. Yep. No. Rearranging the lenses. Okay, good. Let's continue. So that was that's a very simple thing. I can also get a bit further in here because yep. Oh, finally a question, Miriam. It's me, Miriam. Yeah. Yes. Go to the microphone. It's right beside you. Or Lionel will be happy to bring you a microphone. Hint, hint. No, it's not turned on. Too bad. But for the benefit of our listeners over Zoom, I guess would be helpful also to have a microphone. Yeah, you please ask loud, and I'm going to read.
Okay, so my question is simple. So the tracing scope, it's any like a Python code, like at the function level. And also when you are printing out the variable, or like what is the scope of a program states that you could access?
Oh, what is the scope of the program? The scope is the scope of my local variables is just as usual. I'm getting access to the local variables, and I can invoke any function. I can also invoke could also go and invoke the main function of some Python code and execute the main memory, execute the main function, and I would get everything in scope just as you would have it during regular execution. So the tracing does not interfere in any way with the actual execution of the program. If you use NumPy and turn on tracing, you're in for a big amount of data. Because yes, you can. What you don't get is tracing of the native C code. That's right. So it stops at the C code, which probably is a good thing. Yes.
So hello, Steven from SIT. So I thought that you were kind of talking about the old Eric Bodden group, or people like me, like writing really tons of code to just evaluate something for a paper. Actually, the question is whether we also need to think about paper evaluations differently as a research field. Yeah. Because we published something on Android, for example, and we were talking about, let's say, topic X doesn't matter. And someone was like, and how do you deal with reflection? How do you deal with ICC? How do you deal with an alien invasion? And you're like, well, this is not what we're doing here. And so if we're then trying something simple and, hey, we have a Python prototype to evaluate it, I think this is a totally different direction than people tell me, and this also needs to be able to cook coffee, because this is also something that Android can do. And so many reviews are actually pushing us back into a place where we have to deal with stuff that we're not remotely interested in, but to cover the topic completely. And this is point A, and point B, I think. There is one very extreme variant if you want to go into fuzzing, if you're going to Windows programs. The problem there is whatever you try out on something reasonable tends to suddenly fail when you're going to Windows. So even having, let's say, 5 test programs sets you back half a year, because you have to dig into all of them using a disassembler. So yes, doing this in Python would be very nice and easy, but the question is, should we also think about this as a field and say, okay, he wants to solve problem A, he wants to get away, let's say, from code coverage, instead, let's say, explore memory boundaries, and someone will eventually need to put in the effort to do this on closed source Windows code, but it's not that guy who wants to have a PhD. Just throwing in a couple of ideas.
Thank you very much, Stephen. The answer from my side is no. Now the question is, what was the question? But I'll come to that at the very end, okay? At the very end, and it's not far. But let's, for the moment, let's use this as a tool for prototyping, and let's use this as a mechanism through which you can very quickly implement and try out algorithms and use them on small pieces of Python code to see whether they work. Okay, because for instance, for dynamic analysis, a tool like this is going to give you everything you need. Whether this is sufficient proof to show that your new approach, your algorithm works, okay, and whether for this we have to make it run not only on Python code but also on C code is a very interesting question, in particular given the importance of, say, Python in industrial environments. And the question is also whether we as academics actually do have the duty to actually implement things ready-made for industrial usage. Okay, and yes, it does not support syntax highlighting, and it does not support whatever, a shared memory in Windows 95 and whatnot. Are we really supposed to do all that? Why should we do that? Okay, I'll come to that in a moment. For the moment, since Stephen here discussed how he and his co-students worked for a long time in static analysis, let's switch for a moment to static analysis and how that works in Python. And yeah, well, I look at your face as much as I can from here on and to see how you're going to react to things. So static analysis means we're not analyzing the execution of a program, but instead we're analyzing the actual code. And yeah, that's very, very simple actually that's actually very, very simple in Python. Because what you can do is you can very, very easily turn any program, any Python program, into a tree structure, which in program analysis and compiler construction is also known as an abstract syntax tree. The way this works is as follows. First, we're going to convert the source code of our program into a string, and that's actually also just one line of code. So I'm just going to take the function, and there's a function called inspect.getSource, which gives us the triangle source. So this actually now is a string. Let's see, triangle source. There we go. It's a string which actually now contains the actual source code of our function. And now I can parse this into a tree, which I'm going to do right now. Triangle AST, here we go, wonderful. Oops, no, sorry, this is not what I wanted to have. Here we go, let's get some space here. Triangle AST is equal to AST.parse. Is that all I can do? Don't I need to have, oh yes, I need to import AST first. Huh? Too bad, import AST, here we go. Ha. So AST.parse, that's all you need for that. And I think this is pretty much it. You put in this triangle source, and then what you get out is a tree. Wow. No, sorry, this was not what I had. This is what you need. Okay, good. You have a tree, and the tree is in this variable called triangle AST. This is what the tree looks like. Yeah, not very helpful, right? This is about as much information as you get from your average C++ program. We're going to do things a bit nicer because we actually do have a function for visualizing ASTs. I'm going to put in show AST for triangle AST. And after a second or so, I get a full-fledged tree representation of my program. So the triangle AST actually consists of a function definition at the top. And then we have a triangle. Well, that's the name of the function definition. There's arguments. There's 3 arguments named A, B, and C. And the actual code consists of an if statement, which compares A against, checks whether A is equal to B. And if it is, then, I guess we just, we go to the next if, and then it compares B against C. And if there is, and both of these, if both of these are true, then we get to a return node, which returns a constant, and this is a string constant named equilateral. Those of you who've ever been into program analysis, in static program analysis or compiler construction know these tree representations. And thing is, you can easily, and thing is, if you want to work with actual programs, you can very easily traverse these trees and check. Well, for instance, you want to know how many different variables are there in my code, how many different equal signs do I have. This is something that you do, of course, after parsing. So you traverse that tree and, for instance, count the number of EQ nodes, and then you know how many comparisons there are. Or say you want to do mutation analysis. Mutation analysis meaning that you actually change individual parts of your code into other things. You have a tree representation like this, which means that you just swap a tree against another tree, or you replace individual numbers in here. This is all very, very easy. And just because we can, we also can come up with a little function in here that actually traverses the tree, because life is so nice. And then we can, I'm just going to copy and paste this thing again, because I'm a really, really slow typer. I hate my life. So this is a function that collects all the conditions. It traverses the individual nodes. And if the node happens to be an if node, then you can actually also unparse these things. I should actually really show that, because if you go and unparse a triangle AST, you get a string back that actually was the original code. So you can actually transform trees into, you can actually transform code into trees and trees into code back again all day long with a simple call of a function. You have a question over there. Be loud, and I'm just going to repeat the question if I can. The question is, can I use Python to do all these things on C programs? And the answer is no. Well, static analysis, you may be able to. You can probably write your own parser for C. And then you have a tree representation, and you may also be able to unparse it. But for C, all these things are much harder, because A, parsing, in particular industrial C code, is still a huge challenge. Actually, last time I checked, you had to buy something for tens of thousands of dollars, a working parser. Second, there's a preprocessor, which you have to invoke separately. Third, if you unparse things again, things will be preprocessed and it will not look like your original code. So it's hard. If you work on Python, easy. 20 seconds. Do this on C, 4 months, 5 months, depends. Yeah, you need to go to the microphone. I can't hear you from there.
Hi.
Yep.
I'm Pascal from Purdue University.
Hi. Yep.
Okay, so my question is, what you are doing, you are trying to do program analysis.
I'm doing program analysis.
On a program written in Python.
Mm-hmm.
You are doing program on a program written in Python.
Yep.
Can you use Python to do program analysis on a program written in C?
No.
Okay, so if you are trying to build a prototype for your research, but then your target software is not Python, is C.
You shouldn't.
Okay, but
you shouldn't.
Our research is based on C.
No, you shouldn't, because, and that's what I'm trying to teach you here. Because if you think, okay, my target language is C, okay? Or why not C++? It's even more complicated. Then you think, okay, Then I'm going to need whatever. I'm going to need a pointer analysis, a data flow analysis, an information flow analysis from API to whatnot. Yeah, all this stuff, yada, 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 gone. Okay, good. You're at Purdue, right? Okay, good. Purdue, you're lucky. Your PhD advisor probably already has a couple of packages up your sleeve that previous PhD students have suffered through building that. Okay, good. Now you think of, okay, let me design a smarter points to analysis because this is going to make my analysis more precise and whatnot. And then you're sitting there with your C subjects and everything, and it's going to take it's going to take you months figuring out how to do things. And then you're going to then it's going to spend you another couple of months figuring out which approach is the best. And you have to implement one after the other in a language that's super hard to do. Okay, in the end, you will come out victorious. You will come out of the jungle. All your clothes are ripped apart, but you were the one. You are the heroes, okay? You will come out, and from left and right, your fellow researchers will come at you, hug you, fall and bow before you, kiss your feet, whatever. You are the hero because you've done that. Probably you even spent nights in the office doing all that. Yeah, you did all that. There's lots of glory in that. You did this thing which is horribly complicated. Okay, the alternative is you try this out on Python first. Try out which of the many alternatives, design alternatives you can try out, and you can build. Well, Python doesn't even have pointers. Okay, bad example, but you can try out one alternative after the other. Each alternative is going to take you maybe an hour or so. You can even have them all documented in a notebook. You can create a long evaluation for all that. Can compare them, and later on you can even write a paper about how you do, about all the different alternatives that you considered, with all the different numbers. You can do an ablation study, nothing like that, okay? All that. And after you have decided which approach is the best to do, well, then you can go and implement it in C, and then you know what to do from the very beginning. This is what I'm trying to tell you. Abig.
Yeah, hi, Andreas.
Yes.
So I was thinking somebody will ask this question, but
Go
since nobody did, let me ask it. So one way you can do academic prototyping of program analyzers without kind of having everything ripped off while still keeping your jacket on would be to use data log. So you can, data log is a well-known substrate for writing program analyzers. And you can also write like the fixed point computation in the analyzer quite easily in Datalog by matching the fixed point semantics.
Mm-hmm.
And you can also write analyzers, say analyzers in Datalog for C programs, and accordingly transfer the results back to C.
Yep.
So I was just hoping you could comment your approach just a little bit with respect to that, because
there
have been projects on this.
I would love to. I would love to, but I don't have much experience with Datalog. So up to you to do a tutorial next year at ESEC.
There you go. You got your job cut out for you. Andreas, thank you.
Hi, Alex.
The tutorial, the ongoing tutorial. So I had a question, is kind of a follow-up because I was thinking about the same thing. So there are some things that you cannot prototype this way, though. So as you were mentioning, so let's say that I work, my research is a pointer analysis for large C programs. I'm not going to be able to do it here. So I was trying to understand what is the scope here exactly. So what are the kind of prototyping, the kind of research for which you can do easily prototyping this way, and the kind of research for which you don't? Because I mean, I can see a lot of topics on which you will not be able. And kind of a follow-up, if I can ask two questions for the cost of one.
You want to? So
yeah, go ahead.
Just out of the top of my head. You want to do any kind of dynamic analysis, this is it. You want to do any kind of code transformation, say mutation analysis, for instance, or transforming code, refactoring code, whatever, automatically, this is it. You want to do any empirical analysis, say I want to count how many instances of yada 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 you find in Python code, this is it. You want to do analysis of class usage in Python code. You want to do analysis of how student programs evolve over time. You want to figure out which program structures are associated with performance problems whatsoever. This is it. You can get this done in hours. So just to give you a couple of things out of my head, okay?
But you're still very much constrained by the fact that you're only the only language you can handle is Python, correct?
I don't see myself constrained there. I see myself liberated in there, but yes. Sure.
It's a liberation and the constraint at the same
Yes,
time, I think.
yes, but
Because,
this
for
is-
example, you teach Java, right?
No,
Then, no, I say if you teach.
Well,
if you teach Java, you have to teach Java.
I certainly can invoke my whatever static. I can certainly invoke my static void main string arg system dot something print out the dot system print line something, right? Is it it? Yeah, sure, I can do that. I can also do Python and just print, but yes, fine. Yeah.
So the follow-up question was like, would it make sense? Because the reason why this is so powerful, well, part of it is because Python doesn't have some constructs that are problematic, like, direct memory management, I guess, in C and so on. The second one is that because it happens to provide all these nice primitives.
Yeah.
So would it make sense to have somebody, which is a conversation that's been going on for, 20 plus years, right? If you build the right layer, then you can build any analysis easily.
You could also go and create. You can also create an infrastructure for that matter
Right.
that actually converts whatever your C programs into data log or into integrate C or C programs into data log. You can provide some Python functions that allow you to glue all this together. That gives you the appropriate primitives and writes them back again. This is all possible, except that the things that I'm demonstrating up here are part of the Python standard library. They will be around. They're documented. They will be maintained. They will be around. This is not a project. This is not stuff that some PhD project, some PhD student at some place has built at some point and then forgotten about it. No, this is going to be maintained forever.
So I guess your main point is really the fact that this works well, and you're really excited about this and you're selling this because this is part of Python. So Python comes with the capabilities.
Yes,
they're going to be guaranteed to be maintained.
My point is before you try out all your new ideas on a huge C/something whatever infrastructure, try them out in some language where this experimentation is much easier. If it's Python for you, then you can be very lucky.
Okay, I'm gonna let Abik and then I have.
No, I just wanted to add that thanks for the clarification about the class of problems. So that would be actually different from the class of problems for which the data log encoding would be very well suited.
Yep.
Data log encoding is very well suited for the static analysis kind of problems. Yeah.
So let me get back to my code for a moment because I'm extending my 20-minute promise here. But I'll keep on asking questions, folks. That's very, very helpful. This does not need to be a discussion among program chairs and senior gorillas in here. So please, happy to have any questions you like. What I brought up here and what you have had an opportunity to study in the meantime is a simple function that traverses traverses a tree. It checks whether a node is an if node, and if it does, then we actually take the condition that is in here, the condition of the if, and we append it to a short list. And then we traverse all the children. This is simple recursive descent over the tree. And then we do this on the tree and we return the conditions in here. And if I do this on my triangle, not AST triangle. See, there we go. Now I have collected all the conditions in my program, and now I know which conditions actually exist in my program. So this was a bit about static analysis. This is very simple. Well, it is also a simple example, I have to say. So now let's go into a bit, let's crank things up a bit. Let's go into symbolic reasoning and constraint solving while we're here. Okay, so let's do this. Symbolic reasoning, what does that mean? Very simple. We have all these conditions here. We just extracted them. And since we know these conditions, we know that by selectively fulfilling them or not fulfilling them, we can find values that actually cover all these different conditions. If, for instance, I solve the first and the second condition, then I need to find 3 values for A, B, and C, which are identical, and this is then going to cover the equilateral branch in my program. How can we find 3 values that are identical? Well, as humans, we can. For a computer, this is a bit harder, but we do have a magical tool for that, which is called a constraint solver. We're using the Z3 constraint solver from Microsoft, Nikolai Björner to be and his team to be precise. Anyone ever worked with Z3? Raise your hands, please. Whoa! Hey, I didn't kid you not. This was 6 weeks ago. I was in a room filled with PhD students in security. And I showed them a similar example, such as this one. They had no idea how to analyze a program. They had no idea what a path condition is, or even how to extract a condition for an if. No, what they knew was how to encode some problem such that it fits into the well-known AFL fuzzer, and how to decode the output of AFL into their specific domain. They have no idea how a tool like AFL or a fuzzer even works. Okay, this is how you do papers this is how do you papers in security, or at least this is what the security students had in mind. Was a bit depressing, I have to say. Good. So you know Z3. So what I'm preaching to the choir here, but I can tell you something very simple. I can give you something very simple in here. So we go and define 3 symbolic variables. We have an A variable. We have a B variable, B, and we do have a C variable, C. There we go. Wonderful. Ha. And now I can go and invoke a solver. S equals, that should be Z3.solver, right? The Z3 solver. Is that correct? No, it's actually solver with an uppercase S. Here we go. Now I have a solver. And now I can add constraints to the solver, which I would very much like to be solved. And for this, I'm saying, okay, let's make this an AND conjunction. And I want that A is greater than 0, and I want that B is greater than 0. A and B are symbolic variables now. And I also want that C is greater than 0. Why are we doing this? Well, simple thing. A triangle only has positive edges. If you have a triangle with a negative edge, with a negative length of one edge, that's a very interesting construct, but doesn't relate to anything we know from geometry. This is something I have learned because in the beginning I forgot to add this constraint. Then I would get results such as, oh, the triangle must have a length of -1, -1, -2, which is not what you want. Okay, good. So that's basics, preconditions. There we go. And now you can actually go make things a bit more complicated. You want A to be not the same as B, and you want B not the same as C, definitely, yes, of course. But you want A equals to C, so that's that would be an isosceles condition. So A is equal to C and B is not equal to these 2 values. There we go. Ah, this works, I love it. And now all you need to do is you check the whole thing. And you check the whole thing. This means the solver checks whether there is a solution for these constraints. And the return value is set, meaning that is, yeah, the solver tells you this is satisfiable. There is a solution. Great, wonderful. Problem solved. There is a solution. Problem is we don't get the solution yet. For this, we need another extra invocation. And for this is called a model. Here we go. And this is the model, the witness that the constraint solver produces for us. And it tells us that here's a possible example. C equals 2, A equals 2, and B equals 1. And you will find that this actually satisfies all the constraints, namely that A is equal to C, and that B is definitely different from the others. Well, we can also continue doing that. What happens if I do this? That's very interesting. If I want B to be equal to C and A equal to C and A should not be equal to B, what am I going to get? Let me know. Is this satisfiable? Can I satisfy this? No? No? Okay. You're as smart as the Z3 solver. This is not satisfiable, of course. Okay, good. And then if it's not satisfiable, there also is no model. Okay, good, I get that. But if you give it, say, just these 2, is this satisfiable? Yes, okay, great. Let's see it. No. Oh, I keep on adding things here. That's a bad idea. Let me initialize this again. Now it's satisfiable. And here's a simple example. A equals 1 and B equals 1 and C equals 1. Okay. Now, now I can actually take these values and feed them into my triangle program. And if I feed them into my triangle program, I will actually go and check all these things. I will actually go and find out that I'm now covering the case where this condition here, these two conditions are satisfied. Now comes the third part, and now I'm going to cheat a bit. We had these conditions extracted from our triangle program using static analysis. And now we want to actually satisfy or not satisfy these conditions one after the other. How do we do this? Well, I am going to cheat a bit because I'm not going to type all of this in right from the very beginning, but I have written a little program in here. It has taken me 10 minutes to write it, so I apologize if I'm not going to demonstrate this right away. And this little function in here goes and collects all the individual conditions that exist in a particular tree. And I'm simply going to illustrate what this actually is by successfully invoking it, because I can just go and say, okay, collect path conditions. And these are the conditions that I need to fulfill in order to satisfy all the individual branches and paths in my triangle program. Here we go, collect path conditions. And you see what this produces is a list of conditions that are already formatted as Z3 constraints. And what you see here is I need to satisfy one case where A equals B and B equals C. This was the last one. This was an equilateral one. And I need to have a situation where A equals B and B is not equal to C and so on. And these are the 5 different cases I have in my triangle program. Okay, there we go. Now, what we need to do in this, what we need to do here is for each individual element in this list. Oh, let's keep it a bit open such that we understand what we're working with. Here we go. Now what I'm doing is for every single condition in these conditions, there we go, I'm going to invoke a solver. We've seen that before. I'm going to add the constraint, well, from above, that these 3 numbers actually are supposed to be greater than 0, otherwise havoc will follow. And that's a bit that's a bit nasty. I am going to, is that actually sufficient? Let me see. Oh yes. Okay. Now I'm going to evaluate what happens if I invoke check on one of these conditions. So I'm adding a particular condition, path condition in here. So that's a bit of Python magic in here. I'm creating a string which invokes s.check on the given path condition, and then, oh, actually should be s.add, isn't it? Just one. Oh no, you don't need this. You can just use s.check together. Oh well. Oh yeah, that's perfectly fine. I'm just going to. No, that's fine. S.check. You can just add a path condition in here, and I'm invoking eval on that, meaning that this s.check together with this path condition in here will simply be this, which means that this path condition will simply be added to my solver, one after the other. And I think with that, we are pretty much done already. Now, all I need is a model. There we go. And then, well, I can actually invoke the function with that very model. So I'm going to invoke triangle with the model of A as long and as a floating point number. Then we need m.b as long, and then we need m.c as long. There we go. Boom. I think this should be it. Are we right? Guess so. Okay, good. Wonderful. Let's see whether this is going to work. No, it doesn't work, of course. Print M, yada, 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 triangle. Okay, I was never closed. There we go. Oh, boom. And now what we have done is, for each of these 5 conditions here, which correspond to the 5 different path conditions, the 5 different return values in my triangle program, we have invoked the solver to find a solution for the very constraint for these path conditions. And we invoke, that is, we test the triangle program on these individual values. Meaning that by pure static analysis, we now have generated 5 test cases, which come with appropriate numbers in here, and these cover these 5 individual branches in my program. Now, now, of course, well, this is symbolic analysis, this is path conditions, okay? So next thing you're going to ask, what happens if I have a loop in my program? What happens if I have recursive descent? What happens if I have yada, yada, yada? And yes, yeah, sure, these are all the challenges of using a symbolic constraint solver when you're trying to generate test cases. But here again, suppose you want to, in order to analyze, in order to find good constraints that actually, in order to find good constraints that allow you to traverse a loop or not traverse a loop or traverse a loop n times, you need to find a so-called invariant for that loop, which is a hard problem. But how are you going to find invariants for that loop? This is, well, it's actually an undecidable problem. But now you want to try out, well, does strategy 1 work? Does strategy 2 work? Which of these strategies are going to work? And you can try out each and every one of these individually, and you can check how long the constraint solver is going to take and how well it's going to work. So this is not saying that I'm suggesting, so likewise, if you want to say combine symbolic path condition solving with some new variant of search-based testing, or you want to combine it with, well, who knows, some machine learner thing. Hey, just do this for plenty of Python code. Learn path conditions from them. Do an empirical analysis on the complexity of path conditions. Learn what the path conditions are. Use a machine learner to predict what path conditions could be. Use a machine learner to generate the test cases together with some novel neurosymbolic whatsoever. Zillions of opportunities for research. How do you know what works and what doesn't? Yeah, you go and run this right in your, you run this right in your Python program. You run this actually even better right in your Jupyter notebook, because one thing that Jupyter notebooks are really great at is conserving the values of experiments. So you see that we actually have saved all the previous steps that we have gone through. We can go back to them. And actually, if I were not simply demonstrating this right here, but actually writing this down, I would also add text parts which actually explain how the individual parts work and everything. And of course, in a Jupyter notebook, you also have ample opportunities for visualization, for evaluation, for automatically running experiments. Oh, this is just beautiful. There's reasons why data scientists love Jupyter notebooks that much. I'm going to give you some examples. Let me just switch over to by sharing the entire desktop here. So here we go, same as before. Now we're going, if you actually go to the ESEC FSE program, you can actually also go and sorry, let me find an appropriate place in here. Here we go. You can actually go and also invoke this chapter on your own, and you can try out things as you like. So for instance, here's an example. This is plots. So this is right from my book on fuzzing. You can just integrate a plot like this and your material. You can evaluate things. You can create the plot. It will automatically update it with each result. Or nicer even, this is a tree map. Yeah. There's a tree map, there's a code which I took from some, I think, a NumPy or like pyplot package. And this shows the distribution of bugs in a, well, believe it or not, distribution of bugs in a Python repository. So the redder a particular package is, the more bugs it has, and you can go and actually investigate things in detail here, and you can go back. This is very nice JavaScript, which has all these animations and whatnot. So you have ample opportunities for analysis of all sorts, visualizations. You also saw the trees beforehand, of course, but you can also create your own. I mean, here's an example. I have written my own visualization in order to quickly explore and document class hierarchies, for instance, boom, and they become part of your document. Or, well, state machines. Here we have state machines. Yeah, why not? You can create state machines. You can create them programmatically, and then you have visualizations of your results as state machines. Program spectra. This is from automatic. Fault localization. Let me see. Oh yeah, here we have one. Wonderful. Program spectrum. This is Alex. This is Mary Jean Harold and Jim Jones and John Stasko. The redder a line is, the higher its correlation with failures. Well, picture that and, well, guess where the bug is. That's very, very easy to implement. Dependencies, yeah. Here's a visualization of, visualization of data and control flow in slices. You can create a piece of code that visualizes things for you. Why are we actually stuck with, command lines and terminals that act, or even IDEs that act as if we still had terminals as in the 70s. So that's, I don't always understand that. And now the nice thing is, you see, you can combine all these, you can combine all your code in here, all not only showing what you did, but you can also put up all your experiments and all your results into a single notebook. Which means that this is something that you can publish afterwards. This is something that you can hand, this is something that you can hand over to reviewer 2, who asks, where does this particular value come from? Hey, here's my code from the raw data down through all the evaluation steps. There we go. This is the result we get, and this is the plot we have in the paper. If reviewer asks you, what happens if you change that hyperparameter? We'll give them the notebook, and the reviewer can change the hyperparameter. There we go. This makes your work much more replicable, but not only for third parties, but also for yourself. Not so much for you as an individual PhD student, but in your group. In your group, this makes things far more replicable, because the next student, or the bachelor student, the master student who's working with you on that, the TA who's working with you on that, they can take these notebooks and immediately start experimenting with things. And while you, at Purdue, at MIT, wherever you come from, while you in your PhD work, after you figured out what to do, then work on building this big experiment for C programs, re-implement the parser and whatnot, and then in the end still come up with this big pile of code which is hard to use and hard to understand except for yourself. The gist of your work will still be here in that notebook, which captures your basic idea, an example of how to use it, and even experiments, how you compare them, how you compare things against each other. And this is, and this is something I wish I had had 20 years ago, or may possibly even earlier. And yeah, we could have saved lots and lots of time, and it would have saved so much time for students to run the experiments. Would have saved time and students to figure out what works, and it would have saved time for my own students to build on the work of others, and of course for others in the world to build on our own work, or for us to build on the work of others. Because the basic idea and the basic algorithm, this is what gets captured in these notebooks together with their explanation and all. And this does not get hidden under a huge This does not no longer get hidden under a huge truckload of machinery, all the details you need to get things done. Here's the basic idea, and it's small and it's short, and this is where I have it. And this is, we found that these notebooks have a far longer shelf life than all the big infrastructures that our students are creating. And that's also something in the interest of science that we need to work on. Which also means that, so for us, this is now the standard procedure. We implement first things as a notebook, check whether something works, check out the alternatives, find out whether approach A may be better than approach B or whatnot. And once we have it right, and not before, and once we know it works, and once we know that it works better than whatever we want to work, whatever the alternatives are, then we decide, are we going to implement this for some other language or for some larger environment and whatnot? Hey, we may even make money with it in the long run. But one thing I'm still looking forward to see is 3 reviewers whom we sent a paper. We tried this out on 1,000 Python programs, and it turned out everything turned out to be very easy, and we were all done in 2 afternoons. And here's our results. Please accept this for a conference like this one. Is it true that we have to suffer to get our papers accepted? Is it true that we have to go into the jungle and come back victorious and with all our injuries, and now we can finally be on the stage and we've been there and fought the dragon and we're back again? Is that what makes scientific progress? I don't think so. I think the scientific progress is in the original idea and the idea being well conducted. And if it takes you a week to build it, or whether it takes you 6 months to build it, shouldn't make that much of a difference. But that's my personal opinion. If I'm reviewing your paper and you send me something, oh, we evaluated this on 10,000 lines of Python, for me this is actually a reasonable decision rather than doing it on whatever 10,000 line of Ada code or Fortran code, just because it's even harder than C++. You can come back even more victorious, or more foolish. But I think we have to get rid of this macho culture of us going out there and come back with whatever, the crocodile around our neck. Finally, yeah, we vanquished the monster. This is much of this is wasted time. And if your approach in Python or prototyped really works that well, up to anyone, also in industry, to get this to run and to make a commercial product out of it, just as it always has been. Okay, and this is essentially things that I wanted to give out to you. There's things which are going to be harder. If you have anything related to type checking, most Python code will not be annotated with types. So if you want to do an empirical study on how programmers use types, Python is not going to be representative, well, except for Python, that is. We have a paper on the evolution of Python types right here at ESEC FSE. Michael Padel got a distinguished paper award for it. So check this out. If you want to do anything related to program proofs, Python is a bad language because if you want to predict what a Python program is doing, the best way is to run it. And yeah, because there's plenty of things that programmers can do in Python that seriously are damaging the semantics of any language. So if you count the quality of code by the number of WTFs that you see, yeah, Python can have a couple of surprises. But all that, you can try it out yourself. Run your favorite Jupyter notebook, try out the examples, which I just showed you, get into what it means to analyze Python code. And yes, try it out yourself and start building prototypes. Thank you very much for your attention. It's been a pleasure to be here today, and I'm happy to take even more questions. Go ahead, raise your arms, come forward to the microphone. Thank you so much, folks.
I'm a program chair next year. Am I allowed to ask a question? So thanks for the tutorial, Andreas. That was super fun. Seeing that, I guess one of the questions that I have is that as a scientist, right, as we're doing science, we're also trying to build on the work and the ideas of other people. And many, many years ago, a lot of the prototyping that I did in the days of reverse engineering, we used a scripting language and we prototyped our ideas using scripting language. And one of the problems that we hit, or I hit, was that you had all of these, scripts everywhere, and it became a mess, and you couldn't find anything, and traceability was really hard. So how do you, maybe I need to read your book, but how do you address that? Like, how do you address sort of version, I mean, to use GitHub, but how do you document which pieces build on top of which pieces? And,
Yeah, this is, so,
question is clear.
yes. So it is perfectly feasible to use scripting languages to write the most horrible code on earth, and possibly even more so than with regular type languages and compiled languages. But one thing that I have learned to like a lot is to make use of these Jupyter Notebook features, not only to write the code, well, because I see the results immediately and I can have visualizations, that's one nice thing, but I also extensively use it to document my code, most notably in order to write down my thoughts. I have learned over time that when you're debugging something, or when you are building something in your creative process, you want to write down explicitly, let me try out this, let me try that. This only takes you 5 seconds to write that down, okay? Let's try this, and then I do an experiment, and then I get a result. Okay, then I trace back, then I say, okay, this didn't work because I get an exception or whatsoever. So let's try out this other thing, okay? And this remains in the notebook. I can have it in there and it works like in this way, it works like a lab book, as you have it in natural sciences, for instance. I do this experiment, this is what came out, or this other experiment, this is what came out. If I debug things, this is so helpful because I can go back to whatever I had before. And in my creative process as a scientist, okay, this simply helps me making my process far more explicit and far more repeatable. And Jupyter Notebooks are really great in making that. They allow you to, you can use Markdown, which has little friction. You can put in your LaTeX formula as you like. All this, and you can throw in the plots right away when you have your data ready. All this for me is an invaluable contribution. And well, after I'm done, I'm cleaning things up, and maybe even I may also eventually remove the dead branches of the tree in order to explain the whole thing from begin to end. But this is what remains, and this is what I then use to communicate to others. Yes. Yeah. I'll take it offline.
So building on my last point, I think we really have to sort out where research ends.
Mm-hmm.
So there is this one side where you say, okay, if you want to show a new algorithm on Android app, you have to do reflection, you have to do this, that, and that. And where you can say, okay, this is asking too much. But on the other hand, I've seen also people who just build a small model of something and they say, okay, this is great for, let's say, pointer analysis in a lifted binary from a Windows exe file. And I look at them and say, you're proposing this is a suitable approach by putting winword.exe. This will entirely blow up. You'll get hundreds of megabytes of LLVM code. Your approach is crap.
Yes.
So the thing is, people didn't notice that because this was not part of their model. And this was what you mentioned, the old days, where you say, okay, this was actually not what people were thinking it was. The conclusions were wrong from that paper because the model misled them to wrong conclusions. And now we jump from there to way over there.
Mm-hmm.
And the big question for me is, where should we be as a research community? When should we say this is an appropriate evaluation?
Yes. This for me is the key question here. So we definitely should do way more than just writing, than just sketching our approaches in LaTeX, and hopefully it's going to work. Okay, this is one extreme, and the other extreme is, oh, we have built this tool, we have evaluated it on millions of code lines, we have set up a contract with the Department of Defense, we are no millionaires. Dear reviewer 2, what you say to that? Something like that, okay? Well, that's the ultimate evidence, obviously, okay? It's useful, somebody pays money for it. And somewhere in between these two extremes, okay, this is where we need to position ourselves. What I'm saying here is, I think we should definitely, the more mature a technology becomes, the more we should prove that it actually scales, and the more we can also ask to build on, the more we can also ask to build. In particular, when you're coming up with the umpteenth implementation of something, at some point you really have to show, yes, this, and you say, my approach specifically addresses the concerns of whatever, Windows 13, 14, 15, which is with these new features, and this is where our approach is good at. Well, then you either have to model this very, very well in Python, or actually do it on the real thing. And people may eventually ask you to do this on the real thing. But before you do that, you should definitely experiment and prototype. That's my main message here, because that's something that will definitely pay off.
Thank you.
And we have Alex.
It's 25.
So I was wondering, so you show these examples and they're pretty impressive because you know exactly, what the 3 lines to write and so on. So I was just wondering, and what is the learning curve? Because I remember the first time I heard you talk about Python notebook, it was like somewhere at one of the ITIP meetings several years ago. So your group has been working and building on this for a long time. So let's say, I'm sold on the idea and I want to tell one of my students, well, just go and prototype with this. How long is it going to take them to figure out what are the libraries, what is available? Because once you know it, of course, everything comes easy. But in the same way, I could write a suit program and I could impress you by showing you how I can get, a data flow graph in 5 minutes by calling exactly the 5 right APIs to do that. So it's just, basically the bottom line is like, what is the learning curve and how long would it take for somebody to become productive in this
Yes.
context?
So learning Python is something I ask from my advanced students. I ask them to learn this in one afternoon. So if you know any imperative language, Python is not going to very much surprise you. But there's a couple of interesting features that we don't have to rely on it. I know. The tracing is super simple. So all the dynamic analysis, gathering the data, this is all straightforward. Dealing with these abstract syntax trees is tricky, because you're not going to find many examples. Actually, I wouldn't be surprised if half of the code in the world, except for the Python standard library, that deals with these abstract syntax tree, you can find it in my books, because I figured out how to use these interfaces. But this, on the other hand, this means there's tutorials available, say from mine, where you can actually look things up.
If I understood you correctly, you just said before that research should somehow position between the very controlled small-scale lab experiments and industrial applications. Question is, shouldn't we maybe cover the whole spectrum?
Yes.
From simulation up to
Yes.
field studies?
Yes, you should do something that I commonly call the T model. You should cover breadth, in the sense that applying this on as many different subjects as possible. And you should cover depth in order to solve a non-trivial problem, okay? And what we do these days actually a lot is we get the breadth by applying this on a multitude of Python programs, which is easy to build and easy to implement. Then we bite into the bullet and implement this for some large-scale C program, but typically 1-2 programs, not that more, just to show this also can work on a big program. And I'm not saying this is going to work on all programs, but it can scale and it can be applied to these other languages. And I'm not telling my PhD student, build this for all possible C programs. No, do the evaluation where you have things, as you say, small in control. Do this in Python with a prototype, you can try things out. Make a notebook that others can work with and try out themselves, and then build it such that you can actually check whether this would also work on a bigger infrastructure, which again is going to take you a couple of months, and you could go to the jungle and you come back, but then you really have done your homework.
Okay, well. Let's get a round of applause for Andreas for his tutorial. Thank you. And I have a present from the chair.
Oh,
you. So thank you very much. I don't know what
Thank you
that
very
is,
much.
Etruscan.
Thank you very much.